and let's talk about them. This is the stuff I really associated with this class. That's kind of why I wanted to teach it, because I knew this was the sort of more or less hardcore computer science that I didn't really know. I mean, I've been programming computers for my whole life, since before there was any field called computer science. And I never really went back and had formal training in it as they gradually developed the field, and I started in '74. But I knew there was some stuff here that was pretty good. I knew the data structures were a lot of it. So we're going to talk about trees. These things are super important. They're used everywhere. For example, B trees, a version of these, are what's used on the Mac for the file system. And there's a case, if you want to think about a use case of this, that is probably the best use case to think. What if I had 50,000 files in 10,000 folders nested all through the file system, which is the case of every laptop and every computer. And then I wanted to still be able to find something without making you wait 5 minutes while Rover the search dog looks for it. You have to have a much more efficient data structure for storing that kind of stuff, and trees are what you use. So I have some terminology. So a tree looks like this. You have a series of these things called nodes, which are just stored data items, and then you have edges that connect them to other nodes, which is and already it looks like a folder and a subfolder and a sub-subfolder, which is kind of how it works. And this is like the illusory system that you see on your desktop. The abstraction where you imagine you have dragged a file, put it on your desktop, you put it in a folder, you put it in made another folder in the folder, and none of that is true. None of that is how it's really stored on the SSD or hard drive, but it's an illusion created to make the human able to manipulate the files. But this is going to be how we actually store them in the system. And so the root node is the one at the top, has no parent node. All the rest have parents and children. So B is the parent, F is the child, and D is a child. I guess maybe that's E. Yeah, D, E, and F are children. All right. Anyway, so all right, that's the root node, and you can have a subtree. Like FKL, this is a subtree. This could be the root of the subtree and then its children. So you can refer to, in this case, there's a left subtree and a right subtree of the main root. And those are all going to be terms you're going to need. Then you can talk about the degree of a node, which is the number of children a node has. So A has a degree of 2, but B has a degree of 3. Therefore, as we're going to see, this is a tree, but it is not a binary tree. Binary trees, every node has no more than 2 children. And leaf nodes are the ones at the bottom that have no children. And this applies not only to the trees we're making here, but to general graphs in abstract mathematics and number theory and stuff, and they're very, very important. So a parent is a node connected to a lower node, and child are the children of it. So B and C are children of A. And siblings are nodes with the same parent. So D, E, and F are siblings, all children of B. And B and C are siblings, both children of A. Those are just useful terms, and they'll make it easier to talk about what we do in trees. And of course, for a simple tree like this, it's totally not worth the bother. If something only has like 20 or 100 elements, you could just make a list or any data structure and it would be fine. The reason we study them is because you're going to think about really big data structures. Like I say, 100,000 files, 1 million files, 10 million files. How are you going to store that and not waste time? And then it starts making a huge difference. That's why we always talk about the complexity order for large N. Because of course, nothing matters unless you have a large number. You don't need to be efficient unless you're doing something hard. But in fact, we are doing something hard all the time. If you look at what's actually happening inside your computer, you don't notice every hard thing it's doing, but the reason it pauses is because it's really doing something hard, very often searching for something. So this is level 0, this is level 1, this is level 2, and so on, just horizontal levels. How many edges you have to pass through to get there from the root. And the height of the tree is the number of levels, or the number of nodes in the longest path. So here I have 1, 2, 3, 4, and I'm at the leaves. So this tree has height 4. And the depth of a node is how far it is to the root. So B is at depth 1, and H is at depth 2. You need to take 2 steps to get back to the root. All right. Now, this is a nonlinear structure. Now, we've been using linear structures so far, like arrays, lists, stacks, queues, and for that matter, dictionaries. Maybe not dictionaries. Let me think about that. It might be unfair to call those linear. But these are all in order. Stacks and queues, there's an order to the things. There's a top and the bottom. There's a front and a back. You can push things in, and they go at the end or at the top. You know where they go. These are linear structures, and therefore, you can traverse them in one pass. That also unfortunately means that traversing them is a slow process of order n. Typically, you have to run in from the end and go to the next one, although you can jump in arrays. The nonlinear structures are these ones that cannot be traversed in one path. You have this tree structure, and by the way, we don't allow cycles. That's a difference, I think, between trees and graphs. I'm not 100% sure, but I think in abstract mathematics, graphs allow you to have any series of nodes connected by edges, and you can have loops. And you're not allowed to have loops in a tree. You're not allowed to have them in network cabling either, and there's a special protocol called spanning tree protocol to do this. If you wire up Ethernet, and you wire up switches and routers and cable and computers, and then you make a loop, like two cables going to the same switch from the same computer, then there's a protocol that runs. If you sniff the network traffic on any network, you will see STP packets. They are constantly running to detect these nodes and to turn off some of the connections to make it a tree. So, because a loop is really bad for networking. It's useful for fault tolerance. If one of those cables fails, the other can take over, and that's what spanning tree protocol does, but it only lets one of them be alive at a time. Otherwise, your data can end up trapped running around in a circle, freezing up the network. All right, so binary trees are going to be the most important kind we use, and so that's all it is. You have a root node, and it can have 0 children. It can be a leaf, or it can have 1 or 2 children, and that's it. Never any other number. And you have subtrees. So now you have a root node. So the left subtree is here and the right subtree is there. That whatever you take the left child and all of its children are the left subtree. So it's a pretty simple concept. Now a full binary tree, it doesn't allow any node to have just one child. And I'm not aware of any case where you'd actually care about that. But a perfect binary tree is close to what we're really going to use. Here's where you have all nodes filled, all levels filled. So adding a new node, if you want to add a new node to this one, you have to make the tree higher. And a complete binary tree is what we are mostly going to use, especially in the upcoming chapters. This is where you fill the nodes in order. You fill each level before you start the next level, from left to right typically, or whatever. So you wouldn't put anything down here at level 4 until you've filled up level 3. And this will turn out to be very important to make it optimum for use. This will make searching as fast as it can be. Because, you can see it already, if I'm searching for something, I'm going to use an if statement to decide if it's one way or the other here, and another if, so it's going to be log n to find things, if there's some order to it. Then I just have to compare one node in each level, instead of having to hunt through the whole list the way I would if this was a list. All right, and a balanced binary tree is where the two sides differ by no more than 1, which is pretty much the same thing. And here's an unbalanced binary tree. I have all the kinds of nodes on the left, but only one node on the right, so that's not balanced. All right, and so you implement it. It's pretty simple. You define a class node, which is going to give you data stored here, and it's going to have a pointer to the right child and the left child. That will create an empty tree, and then you can just add things here, and this will create, this creates the nodes, and this connects them together, left child and right child. So this is one way to do it. All right, that'll create this tree. All right, and now you have the weird situation of tree traversal. Now it's not obvious how to visit every node in the tree. You can't just go to the start like a list and go to the end. In fact, there's no simple way to do it. So if you start at the node and always step down to the left child, then you only get 3 nodes. You miss these on the right. So there are various methods. You can start from a node, visit every child node, and then proceed to the next sibling. And there are 3 variations of this: in order, pre-order, and post-order. And then there's level order traversal, which is another way to do it. So here's in order traversal. First, you go to the left subtree and you visit it recursively, which means you go to its left subtree and its left subtree. So you start down here at the end, G, when you can't go down anymore. Then you visit the other node, so G, then D and H. Then you go back, recurring one level from recursion, and you do B and E. And that is the left subtree. So you go left, left, left till you hit the end, and then come back one level at a time. Then you do the right subtree recursively, which is going to be, I would think it would be F and then C, actually. According to this, it's CF, which makes me think you must go right and then left. That's why I'm not quite sure. That part I'm not quite sure why you did C and then F. I think it's probably trying to go left to the end. Anyway, then then the root node, and then here. So you do the left subtree, the root node, and then the right subtree. That's in order traversal because it more or less goes left to right. You do the left, the center, and then the right. And let's see if I can figure out from this code why it did this. I wonder if any of you can figure it out. Let's see. On the right, this is in order traversal, always to the left child. That's what I thought. It always tries to do the left before the right, so it regards this as the end because it can't go left, and visits it, I think. And then it goes to this one, then it does the left, and then it does the right. Now then I thought it would still do the right before it did C. So I'm not sure why this isn't FC. That would be more logical to me. I'd have to follow this through in detail to understand why that is. Anyway, it doesn't seem to matter much what's coming next. Then there's pre-order traversal, where you do the root first, then the left tree, and then the right tree. All right? And then there's post-order traversal, where you do the left subtree. Right, you do the root before anything. Here you do the root after anything. Left, right, and then the root. Doesn't seem to me like it's all that important to have these three different categories, but that's the way they are. All right, but this one is pretty important and easy to understand. You just read them in order. Level 0 left to right, level 1 left to right, level 2 left to right. This is kind of obvious way to visit them all. All right, without even worrying about the way they're connected. All right, let me check and see if there are comments in the Twitch. Nothing new? Okay, all right. And so here's the code to do this. If you define nodes to have data left and right, then we create the nodes and then we connect them. That's just like before. Left child, right child, and left child. We just define them manually, so we built this data structure. And then we can do level order traversal, which will just read them across this way. Root node, left child node, right child node, left grandchild node. All right. So binary trees have a lot of applications. Expression trees, we've talked about this in the projects. If you want to evaluate an expression like 4 plus 2 times 3 minus 5, and especially if you've got parentheses, then it can get complicated. So you'll have a tree, and we'll look into more detail. Huffman coding is another technique of compressing data where what you do is you symbolize data items with smaller items, and you carefully symbolize the more common or longer items with smaller data items. And this is what people used to do when telegrams first came out. When telegrams first came out, all the big companies did this because telegrams are expensive. And so instead of sending a phrase like both parties have agreed to the contract, they would just have a short word to stand for that. So it was encoding. It wasn't encryption. It wasn't hiding anything. It was just saving money. You'd send a small series of characters to stand for a longer series of characters, the way people do in chat messages. They have little abbreviations for things like you're welcome and stuff for the same reason. It's just easier to send. All right, and so searching insertion and deletion of a list of items is much better. Like I say, macOS uses B trees for this. So it can very quickly delete files, create files in folders, and find files in folders. It is amazing how Microsoft can't figure it out. I mean, you may not be old enough to remember Windows XP, but I am. Windows XP had a thing called Rover the Search Dog. You would click Start Search, ask it. This must happen to everybody who uses a computer 3 times a day. You save something, then you go for it, and it's gone. It's saved somewhere stupid. I don't know if it went in my Documents folder or somewhere. I can't find it, so I want to search for it. And in Mac, Microsoft had this thing called Rover the Search Dog. You click on it, you play this animation of a dog with a magnifying glass. It would spend 5 minutes searching your hard drive and not find it. And Google, of course, got fed up with this. So Google made an app called Google Desktop or something. That was an incredible app. It would just open up a little tiny box where you could type the name of something. It was like the Spotlight you have on a Mac. On a Mac, you have this. I could just type something like CH1, it immediately finds everything, chapter 1 from one of the classes. You would just do that. You would type the first couple letters or something, it would find it instantly within a second, just to humiliate Microsoft incredibly. Their operating system couldn't find anything in 5 minutes, and done intelligently, it could be done in seconds. And I don't know exactly what the internal structure of Windows is, but I know in Macs to use B trees for this reason. They can find something fast with log time. Anyway, and then the priority queue we're going to talk about here, a version of a queue. This is an application of a binary tree. where you can have not a queue that simply has first in, first out, but you assign a priority to each item, and now the higher priority items come out first. So you have to be able to find those higher priority items. So now let's talk about an expression tree. So if I want 3 plus 4, I have a symbol of this. I have the operator here and the operands down here. So there's infix notation, where you make 3 plus 4. So you do in-order traversal, you do the left subtree and the root, and then the right subtree. So you get 3 plus 4. This is the way we normally write things. And then this one produces 4 plus 5 and 5 minus 3, and then multiplies them. So it's this, but the parentheses are implied by the fact that this subtree is separate from that subtree. All right, and then there's Polish notation. Polish notation puts the operator before the operand, so it's plus 3, 4. And the tree is the same, it's just the order in which you traverse it. This is the prefix. You have to take the top first. And then you can do this one. This will be plus minus 8, 3, 3. So this is pretty confusing. But the minus 8, 3 in the middle is this. And then the plus, whatever that is, 8 minus 3 is 5, so that's plus 5, 3 here. So this is one possible way to write things. And then there's reverse Polish. And you might not be old enough for this. I had an HP calculator when they were new, in like 1973. And they were really fast and they were programmable, which was unheard of at that time, but they used reverse Polish notations. You had to get used to doing everything this way, which I did after a while. You have the operands and then the operators. You want 8 minus 3, you type 8, 3 minus, and then 3 plus to add 3 to it, and so on. You get used to it. It's not bad. In fact, it was a little bit more efficient because the other one had to have an equal sign when you were done, and this one, every operator does the total so far. All right. So you can parse it. You have a stack where you add references to new operands. And then you have a reference to a new subtree when you add a new symbol. So you have a series of stacks containing these arguments. And then you have the new subtree here for each level. So there is a way to build it out of stacks to do this reverse Polish parsing. And so you have new reference add here into your stack. So you can have 4, 5 plus, 5, 3 minus star. And so that's what happens here. Your stack here has the operands, and this has the operations, and it will pull them out. So it pulls out these two and one from there, then it pulls out, takes that one and the next one from here and combines it with the next operation there, and off you go. Just a way to build it. So this is 4, 5 plus, 5, 3 minus, and then star. So it implies the parentheses. It would be easier to understand if you put parentheses around the first 3 and then parentheses around the next 3 and then this. But you don't need the parentheses. They're implied by the order. The fact that there are 2 operands before this means there's effectively parentheses around it. And that's the efficiency of it. Anyway, now we get to, I think, the real punchline, the binary search tree. This is the really useful thing. So this is how you find in applications. It's a binary tree. This is how you store data efficiently, and now you can search, insert, and delete fast, because it's not just a tree. It is sorted in some order, but it's not sorted in a simple order. It has these properties. The value at every node is greater than the values of all the nodes of its left subtree and less than all the values of nodes on the right subtree. All right, equal values, there are different rules for them and you don't really avoid them. So here you have K2, K1, and K3. K2 is less than K1 and K1 is less than K3. That's the idea. So here is a binary search tree. 1, 3, and 4 are on the left of 5, 7, and 9 are over there. Now notice, this looks, you might call this sorted, but if you were to read, it depends on how you read it. If you were to read it, picking this one off first, then it wouldn't be sorted. If you read it if layer by layer, 5, 3, 7, 1, 4, and 9, it's not sorted that way. But it is sorted in the condition for a binary search tree. And the point is, all you have to do to find anything is look at the top node and say, am I greater than or less than? Then you know which path to take. Then this node, am I greater than or less than? So you're only going to have to do log n calculations to find anything, which is the point of it. So this is not a binary search tree because 7 is bigger than 5. So it should be on the right, not the left. And for that matter, 3 is less than 5, so it should be on the left, not the right, and so on. Also, yep, all right. So that's not a binary search tree. It's a binary tree, but it's not a binary search tree. So when you insert new nodes into a binary search tree, you have to find out where it goes. So you start at the top. Is it less than 5? We're going to traverse back down to add something. This will tell me which subtree to put it in. This will tell me which subtree to put it in, and so on. All right, so here's what we're going to do. We're going to put 7 into that tree. It already has 7. Let's see. We're going to start with just this 5, 3. Okay. We're going to add 7 to this, so we compare 7 to 5. It's bigger than 5, so we put it on the right. All right, now we're going to add 1. We're going to build this tree one by one. Now we're going to add 1. We compare it to 5, so it goes on the left. We compare it to 3, so it goes on the left of 3. So that makes the tree grow by another level. Now we're going to, all right, so then we're going to search the tree. So you compare your search value at the root. It tells you if you go left or right. You compare it with the next node. It tells you if you're going left or right. So you only have to make a series of binary decisions, log n, log to the base 2 of the number of nodes to find it. So deleting nodes. If there's no leaf node below it, you can just delete it. If it has a child, then you'll have to swap it with its child. So I'm going to delete this 3, I can just delete it. That doesn't break the tree. But if I want to delete this 2, then I'm going to have to swap the 2 and the 3 and then delete the 2. And that'll work because I know everything here is less than 2, so it's clearly less than 3. All right, that'll work if I have 1 child. If I have 2 children, then I'm going to have to find the in-order successor or predecessor, swap their values, and then delete that node. And we're going to see that. That's a little bit harder, but still not too hard. So here's no children. If you're trying to delete A, you just delete it, and your tree is still a binary search tree. It's still in order. Here, if you have 1 child, 6, and you're trying to delete 6, if you're trying to delete 6 and it has a child of 5, you just delete it and then make this the child of that one. All right. But if it has 2 children, so I'm trying to delete 9 here, and it has 2 children, then what I have to do is find the in-order successor or predecessor. So here, what I have to do is find that after 9, the next largest number is 12. So I have to put the 12 there, swap them, and that moves it down to the node, the bottom, and now I can delete it. So it's a little more complicated. Get a typo out of here. All right. Now, minimum and maximum node. If you want to find the minimum value in the tree, you start at the root and take every left node. It'll always be here. For maximum, you take every right node. All right. These are pretty simple operations. All right, so here's the benefits. This is better than an array or a linked list if you're mostly interested in accessing the elements frequently. Binary search tree is fast for search, insert, and delete. Array is fast for search, but slow for insert or delete. You can calculate where something is by the index, but if you insert something in the middle, you have to move the whole array out of the way. That's an order n operation. But it's not that way for tree. For tree, it'll be a more log n operation. Linked lists are fast for insert and delete, but slow for search because you can't predict how many steps you have to go to find something. You have to go hop, hop, hop down the tree to find it, which is again an order of n. So here's examples. So, all right, so arrays are easy to create and use, and they're the only thing that existed when I started in languages like Fortran. And insert, delete, and insert are all order of n because you have to hop down the list to do anything. It's easy to access elements. You can get complexity is order of 1. You can calculate how far you'd have to move in memory to access every item. And therefore, search is order of n, unfortunately, because you have to hop down the list seeing if the thing is in there. Insertion is slow. Again, order of n, because if you put something in the middle, you'll have to move maybe half the elements out of the way. And the same thing with delete. So that's an array. Now, a linked list, again, linear. You can insert and delete really fast because if you want to insert something, you just add it to the end and connect it in. If you delete something, you delete it, and all you have to do is update the pointers on both sides to jump over it, so you don't have to move any large number of elements or anything. Only sequential access is possible, so you have to hunt through it to access anything, to find the one you want, which is order of n, and search is the same, and insertion and deletion. Insertion and deletion are fast, order of 1. Doesn't matter how long the list is at all. Now for the binary search tree, it's nonlinear. And you see here, what we did is we had some really slow operations, order of n, and some really fast operations, order of 1. But now we got the balance situation. Well, maybe I shouldn't say it. I thought it was going to be all log n, but it isn't. All right, anyway, access, insertion, and deletion are fast with log n. All right, now, if the tree is unbalanced, then you might have the worst case of order n. The tree could just be a list. If all the nodes are on one side, then you haven't really made a tree at all. It's technically a tree, but that's ridiculous. If it's balanced, you're going to have log of n. And again, searching, the worst case would be n, but if your tree is balanced, it's going to be log of n, not that. And for insertion and deletion, this is the worst is n, but again, I think this is kind of ridiculous. I mean, this is if you make a balanced tree, then it'll all be log n. Instead of having some things that are order of 1, some things that are order of n, you can arrange it so everything is order of log n, which gives you a balanced situation. And therefore, the best for general use, where you're going to be adding, deleting, and searching. So to search a list, the list is not sorted. You just have to hop through it, hunting for this thing. That's order of n. In a binary search tree, if the tree is balanced, you use the left and the right equally, then each comparison will cut the problem in half. If it wasn't balanced, then each comparison might only subtract 1 from the thing you're searching to, but if it's balanced, each if statement you make here will make the problem half the size, so it's only going to take the log of n steps to hunt through it. And this is the one I mentioned. The unbalanced tree, of course, is the same as a list. All right, let's try some Kahoots. Let me check for comments. No new comments, all right. Here's my Kahoots, and this is chapter 6. All right, so what feature is required of a binary tree? That should say height. I'll fix that. No more than 2 children per parent. That makes it a binary tree. 0, 1, or 2 children for each parent. That's all. All right. What does a binary search tree require? There's going to be more than one of these. I think it's data stored in order and no more than 1 children per parent. Let's go back to the slides and make sure I got that right. So here's the binary search tree right. So you got to have, the values are in order. They're sorted. That's the special thing. The value, yep, that's the order. This is the other condition. First, you have only 0, 1, or 2 children, and you have the data in order, so everything in the left subtree is smaller than in the root node, and everything in the right subtree is larger. Otherwise, searching is not being made faster. All right. All right, what property is required to make searching a binary search tree fast? It has to be balanced, which means the left and the right subtree are the same height, or only differing by 1. Otherwise, as I said, if it's not balanced, then you're not really cutting the problem in half with each if statement. And that's what you need. It has to be balanced. It doesn't have to be perfect or complete, but it does have to be balanced. The two sides can't be very different in height, or you're not going to gain the improvement, the log n improvement. All right, so what traversal method reads every node from left to right like reading text? The one that suits me, I'm simple-minded. This one I can easily understand. The other one's always confusing. That's called level order. Go through each level, then you go to the next level. All right. And let me mention, it's coming up, but I'll just mention I'm going to be out of town towards the end of the month. The 2 classes will be online only. The 21st and the 23rd, I'll be teaching classes in Utah, but I'll be able to nip out and do these ones remotely. Just want to mention that and get it in the video.